It's my pleasure to introduce Greta Panova, expert in representation theory and more broadly algebraic combinatorics, who will stay with us for a few weeks. Greta is from University of Southern California, and she will give a talk on mysterious Kronecker coefficients. Please.
Thank you very much. It's a pleasure to be here. I need to insert a small correction. I'm more of an algebraic combinatorialist. I would not pretend to be a representation theorist, but that also tells you a little bit what the talk is going to be about. It's about doing combinatorics on things that arise from representation theory. I know most of you guys here like more algebraic geometry. I'm sure there is a way to formulate it in that language too, but I will come from the representation theory symmetric functions. Okay. And so when we were trying to decide what I should talk about, so one of the things that June likes is inequalities. And the other thing I was thinking, well, we should kick off this program with some open problems, right? So we need to see where we are going. So I'll try to combine these two things. It may not, in a slightly unexpected ways, maybe. But before I begin, so the Kronecker coefficients I'll define later in a little bit more context. For now, I have written them over there. That's the only board I have access to. So sorry, guys. It's kind of difficult to see, but they are multiplicities of irreducible representations. What's one property of multiplicity is that they are non-negative integers by definition. So that's an important thing to remember. And from then on, having said that they're non-negative integers, everything else is in that word mysterious. We don't really know anything. So it's gonna be all open problems from now. Okay, but let's start with some inequalities and some simple combinatorial problems. So you guys know what integer partitions are, right? So we represent them as Young diagrams, which are stack of boxes. And the first thing we want to do as combinatorialists is count them. So for P of n, you won't find a nice formula, but there is a very nice generating function. It's not working, this pointer is not working on the screen, but you can see it over here. So what is one property of these numbers that's kind of obvious? They're increasing, right? So, okay, so that's almost from the finish. What's another property? I said there is not going to be a closed form formula, but how large are they? And this is going to go into a little bit foreshadow another part of the talk. There is no precise formula, but there is an asymptotic formula. Famous Hardy-Ramanujan formula, it's telling you that the number of partitions, the integer n, is something exponential square root of n with a constant. So we know at least how large these numbers are when they grow. And of course, this is important if you want to implement something in the computer and test it and all these other things for practical purposes. You need it. Okay. So let's make the problem a little bit more finite. So that's an infinite sequence of integers. So let's now count partitions inside a rectangle. So you have an L by M rectangle, and the Young diagram needs to fit inside. So there are finitely many of those. And is there a formula for the number of partitions of n that fit inside? Depends what you mean by formula, but there is a generating function. That's the Q binomial coefficient. It's a generalization of the binomial coefficient with Q integers. Okay, so what can you say about those numbers? Any guesses? How do they behave? Increasing, decreasing? Well, it's kind of symmetric, right? So the numbers are symmetric, and the first number is 1. And they kind of grow from there, but they are not going to grow entirely. So they are actually unimodal, right? So that's the next best thing from increasing is unimodal, not log concave. Okay, so that was conjectured by Cayley in the 1856, and Sylvester, who was a mathematician in the US at this time, proved it 25 years later. And he was so impressed by himself that he posted the following. I'll let you read it. So how did Sylvester prove it? So Sylvester proved it by the aid of a construction drawn from the resources of imaginative reason. In other words, Lie algebras and SL2 representations. And later, Stanley used first used the Hard-Lefschetz theorem, which you guys probably know better than me. But then he also simplified it quite a bit using a linear, what he calls a linear algebra paradigm. And that was made a little bit more explicit by Proctor later, and Katie O'Hara gave an injective proof of this. So there is like going from these partitions to these partitions, but those injective proofs, they don't really give a symmetric chain decomposition of the partition lattice. So it's not like you're building them by adding boxes. That is not known to exist.
So that's an open problem.
Well, so yeah, the symmetric chain decomposition, I think, is still an open problem. That's not already one open problem. Okay, so what does this have to do with anything that I'm telling you? So let me give you another proof. The difference of two consecutive terms turns out to be equal to a Kronecker coefficient. And what is the first property of Kronecker coefficients? There are no negative integers. So in particular, this is unimodal, and of course these are partitions, so of course this only makes sense when you're up to the middle, and the symmetry is kind of obvious from the description. So one can of course say a little bit more, and I will say this later about the differences here, but just in light with the Hardy-Ramanujan result, the next thing you want to know is how large are these numbers, and actually there is a way to do this asymptotically, which we did later. So there is some kind of a generalization or a version of the Hardy-Ramanujan formula, and which works even for the consecutive differences, which are sort of like a derivative of the function that Pn is. And you can, so don't worry about the C, D, and C and D and the big D are some kind of constants that come out from the limit regime. So this formula only makes sense if you are scaling things proportionally in the limit. Okay.
So here n is at most half.
Yeah. Yeah, so this is up to the half, and afterwards is. Okay. Any questions so far? So, all right, so let me tell you then a little bit about this Kronecker coefficients. So of course, we have the symmetric group. We are probably you all know about this. It's irreducible representations are the Specht modules. They are indexed by the partitions of n, and they correspond. So a basis for module for of shape lambda can be given in some sense to correspond to standard Young tableau, which are fillings of our Young diagrams with the integers from 1 up to n, so they're increasing into long rows and down columns. And then now comes all the algebraic combinatorics symmetric function theory comes into play here once you have this type of set. So then the counterpart of this is the representation theory of the general linear group. These are the reducible modules, are the Weil modules. They're indexed by highest weights, which are also partitions, but not of a fixed integer. They're just like have fixed length, maximal lengths given by the size of the matrices in the general linear group. And then if you want to study that representation theory, one way to do it, of course, is by characters, right? If you compute the characters of irreducible representations, you can do a lot of things. What are the characters here? Are my favorite polynomials, the Schur functions. So the Schur functions, one way is to define them as ratio of two van der Waals-like determinants. You can, but there are many other formulas, and including combinatorial formula in terms of the semi-standard Young tableau. So in particular, this is a positive sum of monomials. And each monomial corresponds to what's called a semi-standard Young tableau. It's a filling of the diagrams with integers from 1 up to n, weakly increasing along rows and strictly down columns. Okay, so one can actually, and from now on, I'm going to forget a little bit about the representation theory because one can work mostly with these polynomials instead. Okay, so the next thing we can do after defining all this reducible representation is take tensor products. And those tensor products are also representations. How do they decompose into irreducible components? They decompose with some multiplicities. And those multiplicities are what we call structure constants more generally, and that's what we're gonna care about. So if we take the reducibles for the general linear group, those structure constants are the Littlewood-Richardson coefficients. How many people do not know what Littlewood-Richardson coefficients are? Okay, so I guess no. Okay, so
I say, I'm sure there are people who don't know.
Maybe I should have phrased it in a positive way. How many people know?
The definition is on your slide, so.
Yeah, so, well, go ahead. So let's see to one of whatever. Like, so that's my story from my grad school. So I had a friend who was doing geometric representation theory, Langland's program, and so on and so forth. Let me not say anything, like and then he had to actually do some examples in computation, and suddenly he ends up decomposing tensor product of two reducible GLN modules. And he's, looking at this thing and like, well, what do I do now? And how do I start writing matrices, whatever. You want Littlewood-Richardson coefficient. And let me tell you the answer. So first of all, you can extract them as coefficients in the ring of Schur polynomials, but you can also compute them. Okay, so there is no nice like product formula or something like that, but there is a combinatorial interpretation. So you're gonna hear a lot more about combinatorial interpretation next week from Igor, but let me give you one example. So the Littlewood-Richardson are counting some types of tableau. Let's not get into the details what the rules for filling up this tableau are, but it turns out that it's a nice thing and you can check it very quickly. So if I give you three partitions and I want to know is the Littlewood-Richardson coefficient positive, all you can do is just draw one of those tableaus that satisfy these restrictions, and then you've proven to me that's positive. There is one, at least. Okay. So what about the Kronecker coefficients? That's the definition again. So now we take two Specht modules, tensor product decomposes into irreducible the same Sn here, so it's diagonal action. So all these lambda, mu, and u are partitions of n in this case. And then we're going to have some multiplicities, which are non-negative integers. And you can use Schur functions also to extract those coefficients, except that this time you take one Schur function, you put all pairwise products of the variables as arguments inside, and you expand it in terms of the Schur functions of each one of them, and you can extract it as a coefficient. So if you want to do some computations for small cases, you can do this.
So where is this formula coming from?
This one,
Yeah.
Schur-Weil duality. So let's, yeah. Okay. Okay, so then what's next? So is there gonna be the next slide of this, the next instance of this? Well, there is no room on the slide, so that's already hinting that there is no combinatorial interpretation. So for now that we know, one thing that we know is that the Littlewood-Richardson are special cases of this Kronecker coefficient. If you take the three partitions to be such that they have long first rows and the remaining parts of the partitions add up. So two of them in terms of number of boxes add up to the number of boxes of the other. Then it actually Littlewood-Richardson coefficient, so they actually generalize. And so Murnaghan defined them in 1938. He was just trying to compute them in his first papers, whatever formula. So he realized this was quite difficult. And then Lascaux and Garcia and Remmel picked this up in the late 70s and 80s, trying to find some formulas, at least for various families. And then Stanley wrote a seminal paper of positivity problems in algebraic combinatorics, which was published in 2000, and he listed this as number 10. Problem, another one there, like number 11, is the Schubert structure constants. So it's there are a family of problems you've probably heard about. And the question is there a combinatorial formula for these Kronecker coefficients? Is there some family of whatever, maybe tableaus, maybe something else that is counting, whose number is giving the Kronecker coefficient? So not that much has been done since then. There are very, very special cases. So I listed some names, but the cases for the families for which we have some interpretation are basically measure zero of all possible ones. But then you can, simplify the question and just ask, when is this thing positive? So it can be zero or strictly positive, and there are already some interesting conjectures. The tensor square or the Saxo conjecture, which tells you that if you take tensor product of two staircase partitions, then it contains every single irreducible one, on which there was quite some work. Then there is the geometric complexity theory, which I'll say in a moment what it is about, but there we care about some special Kronecker coefficients when there are two rectangles and arbitrary ones, and then we could prove some positivity results for that as well, and so on and so forth. So having said complexity theory, they actually show up in computational complexity in two ways. One is that this thing that they maybe don't have a combinatorial interpretation can be formalized in terms of complexity classes. And Igor will tell you next week more about this. So combinatorial interpretation roughly corresponds to being in sharp P computational class. And all we know is that it's definitely not the Kronecker coefficients are not easier than that. So they are NP hard to decide positivity, which makes them already worse than the Littlewood-Richardson coefficients, which are easy to decide positivity for more special reasons that I already said, but they're so for the Kronecker, we know that. And the other side that they show up is they are ingredients in this geometric complexity theory, which is a program to distinguish complexity classes. So, especially in arithmetic complexity theory, permanent versus determinant, maybe you've heard about, and the classes that it corresponds to are VP and VNP, which is another, like P not equal to NP is another major problem to distinguish. And in order to do that, since we are talking about some polynomials, we can use all sorts of symmetries, representation theory and geometry, and boil down the problem to comparing certain multiplicities for some representations, and those multiplicities involve Kronecker and Platism coefficients. Okay, and then the last thing is now we started from the combinatorial interpretation, positivity, complexity, and what can we say about asymptotics? So how large are these things? So we cannot really say much of anything else. Can we at least estimate them? And how do we do this if there are no formulas? So I didn't show you any formulas, right?
So asking about the maximal value for n, or?
For example, so you will see. So I will show you a little bit of various results, what kind of questions you can ask when we talk about asymptotics, and then what kind of answers you can see. And of course, a lot more that is not known. Okay. So any questions other so far?
Do you have saturation here?
No. Fails already for very like case 1-1. Yeah. So 2-2, if you take the triples of partitions 2-2, so squares, the Kronecker is positive. If you take 3-3, 3-3, 3-3, it's 0, and then for odd and even they are 0 and 1. So it fails. The first case, basically. All right. So let's talk a little bit about asymptotics. And I know that you guys are more algebraic, so I'm not really going to go into the details of those things, more like how you can basically get such results without doing any heavy analysis. I'm not an analyst. So why asymptotics, and what is the big picture of the whole thing? So the first natural reason to do asymptotics is that when you don't have any exact formulas, but you need to have some idea of what these quantities are and how they behave, and in particular, when we were doing this geometric complexity theory, that was important because one needs to compare various multiplicities to get inequalities. You kind of need to understand how large these things are. Then there is statistical mechanics, which deals with pictures like this. So this is a plane partition in 3 dimensions. You guys probably have seen this, and now if you can think of it as a tiling model, with 3 types of rhombic tiles, and you can let it go to infinity and say how does this behave, and then there is like random matrix theory shows up here and all sorts of other things. Then there is asymptotic representation theory, which is going to deal with maximal dimensions of groups and all sorts of and various other growth problems. And so, as I mentioned earlier, we kind of need to know if we wanna, let's say, distinguish complexity classes, we wanna understand how big these things are and which one, if we can write some inequalities between them, even if we don't have exact formulas, sometimes you can still try to do that with some asymptotic estimates. Okay, so what is the first result in asymptotic representation theory? Basically, the most important one. So the dimension of the reducible SN representations, these are called F lambda, and these are, as I mentioned, the number of standard Young tableau shape lambda. So I didn't tell you this, but there is a hook length formula. So it's an explicit product formula that gives you that number. And but even before the hook length formula, you have this identity which holds for every finite group, the sum of the dimensions of the irreducible representation squared is equal to the order of the group. So just looking at this identity, and this is just an example of how many things would get derived here. How big is the largest F lambda that shows up? So it's sum over all partitions of n. F lambda squared equal to n factorial. So how many partitions of n there are there? That was Hardy-Ramanujan formula, whatever, some constant e to the constant square root of n. How big is n factorial? N factorial is e to the n log n and whatever other terms. So n log n, c squared root of n, this n factorial is much bigger. So you don't have that many summands here, but the total sum is pretty big. So if you just say that this is greater than or equal to the maximum squared, and less than or equal to the maximum squared times the number of partitions, you already get it sandwiched around n factorial. So the maximum squared is going to be on the order of square root of n factorial. So the maximal dimension is going to be square root of n factorial. And this is, well, one can get it a lot more precise and actually calculate what the shape is going to be. It's a kind of sine arc sine curve that I don't want to write the equation for. So most partitions which are roughly on square root of n factorial, they're going to look like this. And as n grows. And you actually have some bounds for the maximum. So here is another open problem. That the very, very maximum f lambda is square root of n factorial times e to the minus c square root of n. So there is one constant c and then lower order terms. So far we only know c0 is that there is some bound for those. But what's the next order term here is already known. Okay.
Or C1 and C0 like explicit?
Yeah. So there are some integral calculations that yeah, then the reason it works is this hook length formula. You can write it as an integral, as a Riemann, well, it's a discretization of an integral, so you can write a lot of bounds this way. Okay, so what about Kronecker and Littlewood-Richardson coefficients? So that was about the dimension. What about Kronecker and Littlewood-Richardson? So Stanley used basically the same type of soft argument. I told you that this is about roughly square root of n factorial to give of some identities to give bounds for the very, very maximal Kronecker coefficient should be also on the order of square root of n factorial. So it's really big. And the Littlewood-Richardson is exponential, so 2 to the n over 2, the maximal one. And then the question was for what values, for what types of partitions do we get such maxima? And can we say anything more precise? So it turns out that for the Kronecker coefficient to be maximum, you basically need to have all these three partitions have roughly this shape that we call the Vershik-Karov-Logan shape because of the previous result with Hudson. And basically, being near that shape means that the dimension of the representation is on the order of square root of n factorial. So there is an equivalence between these two things, and that's how we characterize this. So it's we determine here that in order for the Kronecker to be maximal, all these three dimensions would have to be in that order. But it is possible. So for every two partitions that are this shape, then there is a third one for which this Kronecker is in the order of square root of n factorial. But which one it is, we cannot say. So there is just an existence at stake. So what about Littlewood-Richardson? So
But
we
you know
can,
that you can have others that are very close to zero, or
yeah,
like
yeah.
like two of these form and the.
And you
someone is
can
of
just
also-
add some boxes like that you don't see in the macroscopic regime. You can just add a few boxes here and there, and then it's not a smooth function in any form, and should also a reason why you cannot really use, for example, machine learning to try to guess or compute your Kronecker coefficients with any precision, because it's changing very quickly. It's not robust somehow.
We'll try that.
People did try that actually.
What happened?
I'm being recorded. No, I mean, so you can just do it for the sake of the experiment, but it's not gonna give you something that you can really say it would generalize for higher dimensions. So you can train a neural network to compute Kronecker coefficients for, let's say, n equals to 13 or 14, and then hope that it somehow works for 15, but there is no, it's probably not really going to help. So the complexity of the network is also going to explode with every end. That's what we expect. Okay, so for the Littlewood-Richardson coefficient, so now let's refine Stanley's result a little bit and fix. So there are two partitions in the bottom, mu and nu. One has size k, the other n minus k, and then there is the big one which has size n. If n and k are fixed, what's the maximum among those? And this is somewhere on the order of square root of n choose k. And n choose k is now exponential, so it's a much smaller number than n factorial. And again, you can say various types of existential proofs that for every sequence of partitions for which the dimensions are maximal, so if you take two of them, then there exists a third one for which the Littlewood-Richardson would be on that maximal order. But yeah, so here actually it's even easier because for the Kronecker coefficients, it's hard to compute once you have big partitions and to say that it's really gonna be zero. For Littlewood-Richardson, we have a Littlewood-Richardson rule, so we can just like add a small stack of boxes to one of the partitions and make it zero immediately. So it's again not smooth, even though Littlewood-Richardson are already much nicer. And so you can also give some kind of next type of bounds. Okay. And is to make connections to, so I mentioned statistical mechanics and random matrices before. There are ways to actually get these coefficients from random matrix integral, elliptic integrals, and say something by analyzing those elliptic integrals. The problem is that, again, the answer is gonna be something inexplicit. It's gonna be some solution to a variational problem that you can't really get the actual constants in the asymptotics out. So you only have, again, rough estimates, and then the answers are still gonna be on that level. So for lambda and mu of certain shapes, there's going to exist some nu for which this is whatever. But if you actually want to have three explicit partitions growing, let's say, in some manner, what's the asymptotics is not three. And I should plug in here that since you guys like polytopes, Littlewood-Richardson count number of integer points in some polytopes, which are not so bad, actually. So it is pretty valid question. So estimating number of integer points in polytopes, of course, it's hard, and volume is hard, and all these things, but maybe here there is something more to say. Oh, a new version of Java is available. Okay, so what about some other regime? So let's say the partitions are not this like very Kirov shape, but are growing in some other manner. So we can get this type of general bound, which is always true, but sometimes it doesn't give anything. When does it give something? So imagine that you have your partitions are rectangles that are very long. So L by L squared. And N, of course, is going to be L to the cube. So then actually the Kronecker coefficient is now bounded by explanation. So how do we get this type of bound? So now I'll show you a little bit what happens behind the scenes. So we use this, let's say, these Schur functions make things very explicit. So there is an identity. So it also has to do with Schur-Weil duality, that if you sum over all partitions, Kronecker coefficient, Schur function in X, Schur function in Y, Schur function in Z, then this is counting, this is the generating function for the three-way contingency arrays, so three-dimensional one, three-dimensional contingency arrays with marginals, two-dimensional marginals on each side are fixed. They are being kept track by these variables, and alpha, beta, and gamma are the three marginals on the three sides. This is number of contingency tables. So this is, I guess, the formal definition up here. So you write this identity, and what do you notice immediately? Well, these are sums of non-negative monomials, and what else can you say? So X alpha is definitely gonna show up if in S lambda if lambda is equal to alpha. So here we have if we compare, if you look at alpha, beta, gamma being lambda, mu, nu, you basically get then the inequality immediately for free that G is bounded by the number of contingencies. And now what's the number of contingency tables? Well, that's already a problem. And there are various results, but the asymptotic is not very precise depending on what your marginals are. There are some results by Barbin. That would give you this, and this maximum you can find if you have some types of nice marginals in general, you know. Okay. What else can you do? You can also take your partitions to have what's fixed diagonal length. So this is what's called Durfee square. And if this d lambda is some constant, then you let the partitions grow in the two directions. So they're gonna grow linearly in some sense. So this is dimension is fixed. Then you have polynomial bounds. In the sense polynomial that this is fixed here and n is your variable that's growing, and you can find those bounds. And in again, you can't really say for which exactly partitions you get the maximum, but there are various existence type of results that there is gonna be something that's big of this order. Okay, and the last thing that's about asymptotics that I wanted to say here is going back to the original problem that we started. So we have these partitions in a rectangle, right? And so it's so we were using various properties of Kronecker coefficients and a bound that comes from a character evaluations. We were able to actually give a lower bound for these Kronecker coefficients and consequently for the difference in the power for the consecutive differences of number of partitions inside a rectangle. But can we say exactly more precisely what it is? And I already showed you this is possible, but is no longer any algebraic. So using actually tilted geometric random variables, we can somehow parameterize this problem and get even the difference using moment methods and so on. So that is the exact bound that was already that I mentioned in the beginning. Again, this D, so A and B are this already given by the problem, but C and D are actually solutions to some integral equations. So again, it's not super explicit, but it's as good as possibly can get. And then the Kronecker coefficient is that difference. It is for those families we have exact asymptotics, tight asymptotics. So that's probably one of the only general results that I'm aware of. Okay, and so this is about asymptotics. And so implicit in everything I'm saying here, there is already everything. So everything else is an open problem. So for which partitions exactly find families, even let's say 3 triangles, Kronecker coefficient of 3 staircase partitions, how large does it get? We know it's positive, so it's at least 1, but how large exactly, there is no, we have no way of actually assessing that right now. So all of these problems are still quite open. So, okay, one thing then you can ask yourself, so we cannot solve a big problem, is there some special case we can solve maybe? Or some other intermediate problem that maybe we wanna solve. So what is an intermediate problem here? So as I mentioned, there are the Littlewood-Richardson coefficients are a lot nicer in various ways. They have combinatorial interpretation, and then the Kronecker coefficients are pretty bad. So what lies in between? So in between lie the reduced Kronecker coefficients. So here is the definition. In green are the Littlewood-Richardson, in red are the Kroneckers. Now these blue guys, the reduced Kronecker coefficients, if we take 3 arbitrary partitions, alpha, beta, and gamma, no relation between them, you can add a long first row to every one of them. And it's actually a theorem, it's not obvious that when n grows, this is stabilizing, and it's an integer. it is some kind of an integer. And it shows up in the partition algebra, so it is actually another structure constant. Because presentation theoretic meaning.
Greta, I'm just a bit confused. I thought you told us earlier that in this setting, the Kronecker coefficient is reduced to the Littlewood-Richardson.
Ah.
You had such a formula on one of the slides.
Yes, so that the difference this time is that, okay, I'll show.
There we go, yes.
Yeah, so only when alpha is equal to beta plus gamma. And if there is data, so if alpha is bigger than beta plus gamma is 0. And if it's smaller, we don't know. But you can still define it, right? So, yeah. So, okay, so it does interpolate somehow. So there is a case where this is exactly the Littlewood-Richardson, and what happens for in the other situations. So Kirillov in 2004 called them the extended Littlewood-Richardson coefficients, hoping that they will have some of those properties. And then he posed an open problem, find a combinatorial interpretation for those. At least if we cannot do Kronecker.
So, but what is that? Sorry, it stabilizes from a certain point, right? What's the point where it stabilizes? So it's, I mean,
It's,
if I give
it's
you
like-
an arbitrary one, an arbitrary Kronecker coefficient, so you perhaps need to extend the first row
Yes.
by how
How
much?
much? Well, so there is, for sure, if you extend it by the size of the smaller partitions, it's already stable. So now, when exactly it's stabilized would kind of depend on what the three partitions are, so it's
Okay.
not, yeah. But
it's a subproblem, right?
yeah,
It's
you
a
know,
subproblem anyway,
you know that from some point on, and you know that for sure this point is smaller than twice the size, the maximal size, or something like that. Yeah. So it is more deterministic than the one. Okay, and so that's another open problem. So using partition algebra techniques, people were trying to study them and find various identities, which there is quite literature on the subject, so we can also think of them as structure constants in various rings and so on and so forth. So the question was, of course, can we actually solve this problem? And the answer, okay. So where are they here on the spectrum? Between Littlewood-Richardson and Kronecker, so somehow people think it's somewhere in the middle. Is it closer to Littlewood-Richardson? Is it closer to Kronecker? Where is it?
Can you please clarify what exactly is really known about Kronecker? I mean, should that also just be a question mark? Do you know that Kronecker, for example, is not in sharp P or something like that?
Not yet, but we know it's sharp P hard, and we know that the deciding positivity is NP hard.
So there is a sense in which Kronecker is really.
Yes, so there
provably
is,
not.
exactly, so I didn't want to go into complexity, but so Kronecker deciding positivity is NP hard. Deciding positivity here is polynomial. So you already have a strict difference, this is worse. And
That is assuming.
no. Okay. Okay. Yeah. I don't know. The universe would collapse. All right. So, okay. So assuming P is not equal to NP, there is a difference between these two. And reduced Kronecker is somewhere in the middle. So where exactly? Well, turns out that the reduced Kronecker is exactly the same as the Kronecker, which is just one identity. So you take an arbitrary. So every Kronecker coefficient can be written as a reduced Kronecker. So of course, every reduced Kronecker coefficient is a Kronecker coefficient by this definition. And the other way, but the other way is also true. Every Kronecker coefficient is some very explicit reduced Kronecker coefficient. What's the diff? How do we get it? We are basically adding these three rectangles to the partitions, and we have this is a reduced Kronecker. And in particular, what does this mean? It means that deciding positivities for the reduced Kronecker coefficients is also NP-hard by what I just said about the Kronecker. That computing them is gonna be sharp-hard because we know this about the Kroneckers, and we don't know if it's in Sharpie, and maybe it's not at all. And then saturation, you were asking about saturation. So saturation fails. Before knowing this result, we proved it separately for the reduced Kronecker coefficients. Well, we disproved it separately for the reduced Kronecker coefficient, but in particular, it would follow from this formula as well. And where is it on the scale? Exactly where, on top of the Kronecker. Okay, so I don't know, do I have time to explain anything about this result? How long do I?
Sure, go ahead.
Okay. So I will show you how the proof works because it's basically 2 slides and it has to do with these three-way contingency tables that should be relatively understandable. So before that, one needs to prove some identities. So if you have 3 partitions and you add one rectangle to one, another rectangle to the second one, and a very long first column to the third one, the Kronecker is the same. So proving that is actually not hard. You can do it with symmetric functions, with this identity here with the sure functions. You just plug in the finite number of variables and you see what you get. So just from the combinatorics of the sure functions, you can actually just cancel some monomials and you'll get an identity. And that's enough because they already form a basis in this set. Now, you apply this lemma twice, including there is a property of the Kronecker coefficient that is the same if you flip 2 of the partitions. So you can apply it twice and then we have this type of identity after you flip. Okay, so what's left to do? So now in the reduced Kronecker coefficient, we are gonna be adding, we don't know whether we're in the stable range yet. So since we don't know this, we need to be able to add more boxes and say that it's still the same. Okay, so that's more or less the hard part. And basically the theorem says that, okay, if you have some relations between the first parts of the partitions and their lengths, then if you add a long stack of boxes to the first one, it's always going to be the same. So how do we prove this? So let's go back to this 3-way contingency tables. Here they are again. So this C alpha beta gamma is going to be the 3-dimensional boxes where we put integers, zeros and ones inside each box, and we want for each plane that the sum of the ones in each plane is given by whatever constraint alpha or beta or gamma is, depending on which direction you take the plane. And so this is a lemma which when written doesn't look very appealing, but what it really says is that if you have your constraints satisfy this type of inequalities, then basically you're forced to have this gray regions stuffed here. So the ones are gonna be all stuffed in two rectangles on the two sides and one really long column, and everything else will have to be empty. And the interesting part will be happening in this blue box. And this is just a simple combinatorial statement. And in particular, of course, if you want there to exist at least one contingency array, then a three-dimensional array, then you need to have various restrictions on what of the constraints in there between them. And that formula I already showed you, although I didn't write it in a generating function type of way, but x, y, and z are three variables that keep track of xi, yj, and zk is going to correspond to the ijk box. And if there is one in that box, you're gonna take that monomial, otherwise you're gonna take the one. And so if you multiply them out, you're gonna get all possible contingency arrays where x, y, and z are gonna keep track of your marginals. And now this is a sure function identity, and now I'm gonna plug in for the sure function this ratio of two determinants formula. I don't have to remember it, but there is a way to kind of invert this identity and say that the Kronecker coefficient is going to be the coefficient in front of some monomial in an alternating sum. When you extract it all out, it's going to be an alternating sum over counting contingency arrays. And then we're going over some permutations. And the constraints change with the permutations. And then the final step is just realizing that if you have alpha, beta, and gamma have whatever extra rows here, these constraints are gonna give you zero. Most of the times are not gonna be possible, except in certain cases. So you need to look at the first constraint on both sides, and then the horizontal constraints on top, and you extract what they are from these formulas, and from the lemma that I just showed earlier, you don't have that much freedom. So if you start varying your permutations, you're not gonna get any possibility. So you're gonna have zero contingency arrays. So you write down your restrictions. And then basically you know that your permutations, the only permutations which give you no zero are gonna look like this. Well, this particular row would be some permutation, and then everything else becomes fixed constant. And you write down the identity, you get rid of the first two. So you get rid of this extra terms, and you get the formula for the original Kronecker coefficients without adding h. Or roughly that's how it works, and you need to kind of draw it on the picture. And that's it.
Thank you a lot. Are there questions?
What structure constants? How do they come up as structure constants of something? This reduced Kronecker coefficient.
The reduced Kronecker coefficients, well, they show up in the partition algebra, and it's Rosa.
Geometrically.
The what?
Geometrically, yes.
I'm not so sure for the geometric link if there is any, but so Rosa Orellana and Mike Zabrocki, they actually constructed a polynomial ring which is not homogeneous, where they would show up as structure constants when you take products and expand in those bases.
Yeah. What's the basic premise of geometric complexity theory? Like, can you say a few words what that means?
So, okay, so basically it's trying to establish computational complexity lower bounds. And we're computing polynomials. So the complexity here is measured in how many operations you need to compute a formal polynomial. So the variables are part of your input. And you need to do some elementary operations, multiplications, whatever, and then you get your polynomial out. So how many computations you do for a given polynomial is its complexity. And or the minimal number of such computations. And if you are doing, so your polynomial, let's say, has n variables in degree most n, then if the number of operations is polynomial in n, this is the VP. And if it's not, but you can express your polynomial as a sum of exponentially many VP polynomials, then it's a VNP. So it's like the, and in order to prove VP is not equal to VNP, we need to distinguish two representatives of those classes. Those turn out to be determinant. Determinant is a polynomial variable matrix, and the permanent. And then you need to say that basically the permanent cannot be computed easily. There is a way to compare it to the determinant, because actually the determinant has some universality properties that everything in VP can be done with by some determinant. Every polynomial can be expressed, and then you throw in, so then you need to compare permanent versus determinant in some more algebraic way, and then you throw in all the symmetries and GLN actions and so on and so forth to consider the varieties that you get, and that's where the multiplicities would come in, because you want to say that one is not contained in the other, and you just want to find a multiplicity that's bigger in one versus the other. So there is a lot going on here, so I'm not sure I can really, but we can talk later.
So I have two questions. The first one is, so we know the Littlewood-Richardson coefficients are lattice points in some reasonably nice polytopes. Is there any hope that something like that could be true for the Kronecker? And the second question is, what is that beautiful place?
Well, so the first question, so if they were lattice points in some polytope, that would be a combinatorial interpretation, and that would put them in Sharpie. So we don't really believe in that, but there is at this moment there is no statement either way. But if there are points in a polytope, that would be beautiful. And in particular, it would mean that this deciding positivity is going to be in NP. So far we only know is that it's NP hard, but it may be worse than NP. But if it's an NP, means that you can just find one of those points and prove that the Kronecker is positive, and that would be really nice.
So have something having a combinatorial interpretation, that's a technical expression, right?
Well, we're trying to make it, but there are different ways. So you can talk about points in a polytope that could be a combinatorial interpretation, or more generally, we say that it's equivalent to being in Sharpie, because in computational complexity, at least you have these classes, you can talk about something not being in that class in some formal way, because combinatorial interpretation, otherwise it's not something you can disprove. And if you cannot disprove it, then how do you know you found it? So this alternating formula that I showed you might be a combinatorial interpretation. So it's combinatorial. It's just not positive, right?
When you say that counting points in a polytope would be a combinatorial, right, so is there some implicit
bound on the dimension of the polytope or some sort of parameters as a function of the
You
input
don't, you don't
data?
want this thing to blow up, so you don't want really a exponential dimension or, yeah. So at some point, if your description is so complex, you might as well just compute them with whatever. I mean, there are exponential algorithms that will give you the number. So you might as well do that. So and we already know that the Kronecker coefficient is the dimension can be said as dimension of some invariant space. So all you can say, oh, it's counting the number of independent vectors. So some basis, but what's that basis? Probably horrible thing to compute. So
Just so that we are in the same page. So when you say that counting points on a polytope is a combinatorial interpretation, you're implicitly assuming that you have a nice description of the polytope.
exactly, yeah.
And
what nice means
what
again.
nice means is
So that's why I'll leave it for Igor next week to explain what sharp P exactly is, but there is actually a quantitative description of what you're having.
Yeah.
And so you can't just, if your dimension is exponential and your constraints are, I don't know. So if things blow up too much, then it's not gonna be there and it's not gonna be useful, right? I mean, in the end, you want this to be useful for something, or if you can't actually compute it in practice.
So I think there are two things: the presentation of the polytope and the fact that we can count their points. Both have to be fast on a computer.
Well, counting the points is still might be exponential. That would still, but as long as you can find one point and say that it's, well, as long as you can say that a certain point is there at least in a reasonable time, then it is combinatorial.
Once we're talking about what can actually be done in a reasonable time, then we've left this realm of computational complexity, because the computational complexity is about asymptotics, right? And so you might have some algorithm of low complexity with astronomical coefficients and some other algorithm that has really bad asymptotic complexity, but in fact, in practice, for the cases that one would actually care about, where the input is not astronomical, it actually runs and gives you the answer you want. So I feel like these are sort of two different questions, like what works in practice and what the
well, but when you
computational-
say in practice, let's say you want to prove a statement for every n, those Kronecker coefficients are positive. So
But then you might not care about the complexity. If you had a description that's sort of mathematically clean enough that you can prove theorems, then your existence.
But you want to be able to work with this description. I don't know. It's a tricky question. So anyway, we can.
Because you could take just a segment of length equal to the.
Yeah. So as I said, so there are algorithms which compute these Kronecker coefficients in exponential amount of time. So. And of course, we have been able to prove various theorems that this is positive and so on without having any practical things somehow from various implicit properties. But that does not mean that we've solved the problem, right?
So less complex question, probably. So like you said that there's a polytope whose lattice point count is a little Richardson coefficients. What about the volume of that polytope? Does it have an algebraic interpretation, like the coefficients or something?
Does it? Actually, I'm not sure. The volume of the.
maybe related, but OpenCove had this result that Littlewood-Richardson coefficients are, in some precise sense, asymptotically log concave as a function of the partitions. Can we expect something like that for the Kronecker coefficients?
Probably not.
Probably not.
So all this, my experience, all the my properties fail already, saturation, all sorts of.
So you talked about Littlewood-Richardson is related to the general linear over C and Kronecker to Sn, but there are other groups, other families of groups. So are there any results of this sort for so the GLN over R or matrices or finite fields?
Well, we
can
do
ask the
have
same
actually
question.
some of these asymptotic results can be done for other finite groups in some sense. That I mentioned, of course, you could use the dimension. The order of the group and so on. There's an input, but you can do some asymptotics also for those settings. But for the rest of these things,
There is no other instance of something that is combinatorial, nice like Littlewood.
Yeah, Q-sure functions, like P and Q-sure functions, and you can do the same thing, but I don't know what you get.
yeah, I mean, that's once you start. Yeah, I guess there are some instances, but it's more special, and more related to expanding products of polynomials rather than actually representation theory.
So I know there's a very interesting discussion, and I encourage people who want to discuss further, but maybe we can thank Greta